This is punch counterpunch with .NET. It was a 10:30 talk. We flipped with the White Rabbit. So I hope you guys are all in the right room. If you got to leave, don't worry, I won't mind. My name is Wolfgang Goerlich. I am the Systems Manager and Security Manager for a financial services firm. In my day job, I occasionally get to write code, occasionally get to play with systems, sometimes even get to analyze packets. Generally, those discussions start something like this. Oh, we really got to let Wolf do something. Because usually I'm doing more of the management, the risk management, that sort of thing. So this is what I think of myself, but I think this is probably more realistic. At least I admit it. People make a lot of assumptions when your name's Wolfgang and you have a beard. So I want to free up and clear up some assumptions right away and actually head off some of the trolls at the gate. Everything you're going to see here is been developed with people with more time and talent than I have. And of course, all the Dilbert art belongs to Scott Adams. I'm really here today just to tell you guys a story, hopefully a very good story. But before we can tell the story, we've got to tell the backstory, right? You got to know the backstory. That's always key. So let's talk way, way back when, long, long time ago. When mankind were in caves, we always wanted to send messages, right? To communicate, to collaborate, to coordinate. We've always needed to send messages. But this was not very efficient, and thankfully with communications theory, they started developing better ways to talk about how we send communications. First innovation was A to B, right? A needs to send a message to B, A to B, A to B. And that was good. That was a great first start. I was much, much better than drawing in caves. But it's also pretty boring. Thankfully, in 1978, there was an innovation, a radical innovation in how we communicate, thanks to these gentlemen, Rivest, Shamir, and Adelman, better known as RSA. And their innovation, it wasn't mutual key exchange. I mean, that was kind of cool, but that's too mathy for me. I got the point here. And it wasn't something that you could buy and smash if you wanted to get a dual security t-shirt. No, it was even something more fundamental than that, something that can't be hacked, something that can't be sold EMC. RSA brought us Alice and Bob. Thank you. Much better than saying A to B. Alice wants to send a message to Bob. I like that much better. I hope you guys do too. But still, we wondered, who is Alice? Who is Bob? How do they know each other? What's the backstory? And this created untold controversy as people argue back and forth. Were Alice and Bob having an affair? What was Eve's role in this? Etc. And if nothing else, if you guys take nothing else from this talk, check out XKCD's take on Alice, Bob, and Eve. Classic Monroe. It's hilarious. But yeah, so we still wondered who was Alice and Bob, and the world would have to wait a long time, more than 10 years, 11 years as a matter of fact, to the next major innovation, on par with RSA. The next major innovation came from Scott Adams, who, of course, in 1989, launched the Dilbert comic strip. And finally, we could put a face to the name. Alice wants to talk to Bob. And they're not having an affair. Bob's a dinosaur. That's gross. Come on now. So now we have Alice and Bob. And yes, indeed, this is progress. So this is the story of Alice and Bob. And I'm going to tell the story in 10 parts, 10 rounds. Because Alice wants to talk to Bob. But of course, there's security. We have to ask ourselves, WWMD, right? You guys have the bracelet, WWMD? You know what I'm talking about? For those of you who don't spend as much time with Dilbert Comics as I do, you may not know Mordek, the preventer of information services, who famously intoned, security is more important than usability. So we must ask ourselves, what would Mordek do? And of course, Mordek's going to stop him. That's his role. That's his job. And heck, it's just fun for him, especially when you're evil. So we really have our cast of characters. Alice wants to talk to Bob. Mordek wants to stop them. I'm going to walk you through 10 rounds, punch and counterpunch, with Alice and Bob. Here's how it's going to work. I'm going to give a demonstration, some applicable code, some notes for the attack and the defense. Not lessons learned. Any learning is on your own, guys. I'm going to give you some notes. It is going to go fast. I talk fast. Some of these demos are fast. So feel free to hit me up with questions afterwards or hit me on Twitter. Except for you. You can't tweet at me. I'm already being trolled, and I haven't even got off stage. So it just gets worse. Yeah, so I wrote some code to demonstrate some attacks. So I'm going to show it to you guys all in canned demos. A little bit lame, but I hope you'll bear with me. So round one, right? So Alice wants to talk to Bob. And we'll see if the videos work. Come on, yes. So what we have here is a simple financial services environment. Terminal servers, right? 3 users, Alice, Bob, and Mordek, logged in. And with the number one, did I mess it up? Yeah, I did. Excellent. 3 users, Alice, Bob, and Mordek, logged in over terminal servers on Windows Server 2008. The number one challenge we have with covert channels is because every time we have a legitimate communication channel, we intrinsically have the possibility, the very real existence, of a covert channel. So here we've got a shared folder, which is meant for legitimate business use, people, not for sneaking out after lunch. But try telling that to Alice. Anytime we have the ability to have a communication channel, we have the ability to misuse that channel. And access controls aren't enough because, of course, we've set up our networks for sharing. So Alice can talk back to Bob and put whatever they want to put in some text files. But of course, you can't beat ice cream. But of course, Mordek can see those files. He can see it. It's all in clear text. He's got rights. He sees the files change. He's a good admin. He goes in and looks. And right now, you're probably thinking what he is, which is this part of the demo is pretty. We got to get it better. That's no good. It's clear text. Come on now, Wolf, what are you showing me? So the next thing we're going to do here is we're going to switch to encryption. From here on out, every single demo, round for round, is going to be AES 128-bit encrypted. She's going to log in and use a simple encryption. A for Alice to send a message, put in her passphrase. She has 32 characters if you want to use it as your AES encryption key. Point it to the file and type her message. Once she types it, that Unicode is going to be encrypted with AES 256 and going to be embedded, AES 128, and going to be embedded into a text file in base 64. Boom. Now Bob will go in, run the same command, enter the same password, of course, because AES is symmetric key cryptography, same passphrase, encrypts and decrypts. And we'll pull that message out. Now, one thing Alice did, she's pretty smart. She read the manual. You got to read Microsoft documentation. So she's using secure string. Secure string in memory, if you look it up in .NET, is awesome. It's hidden in memory. It's encrypted. It's magical. There's rainbows. And so you can't grab that password out of memory. So Mordek's still looking at the file system. He notices, hey, they're still reading and writing. And now we got some weird string that doesn't make much sense. So Mordek could do a number of things. He could try and brute force the crypto if he had all the time in the world. That's kind of boring. What he really needs to do is somehow slow them down, right? I mean, the whole purpose of any good defensive team is to slow down the bad guy. So maybe we'll just screw with the message a little bit. Now you see we get an exception. If there's any encoding off, any bytes or bytes that are missing, of course you can't decrypt, you can't decode, you get an ugly exception. So that's all right. Maybe we'll just keep doing it. Just bang the heck out of that file. I mean, why not? It's fun. It's all good. Mordek enjoys himself too much. So text files are good, but in terms of being a covert channel, the defensive team can see that. That's not cool. And it's not very covert because, again, you can see it, right? So let's take it up a notch. Let's actually use the alternate data stream. The one thing that can be missed in NTFS is you actually have a primary data stream, right? The world above that we all see. But there is the underlying reality. Okay, too much drama. You got the primary stream, and you got the alternate data streams. Each file can have as many alternate data streams as you want. So here we're going to do the same thing, passphrase. We're going to pick a file, which is good, and we're going to put in a chat stream. One for Bob, one for Alice. And what these chat streams are is they're actually alternate parts of the file system that cannot be seen, can't be written to actually with .NET. We'll get to that part in a minute. But it can't be seen with Explorer. It can't be seen with the command prompt. By default, it's pretty covert. So now they can chit-chat back and forth through this file system. And Mordek can't see it by default. He may see, hey, wait a minute. I know that that file's still being changed because the dates are changing. But the content's still the same. So maybe Mordek will screw with it again. He has fun. But because that content is, again, on the primary stream, not on the alternate data stream, it doesn't affect their chatting, which is pretty good. Now, one way Mordek could delve into this is using a tool called Process Monitor. Process Monitor, free from Microsoft for our system internals. Oh, one thing I should say is this isn't a demo pitch, so as much as possible I'm sticking to free tools. A couple are trial, I'll point those out. But Process Monitor, free tool. And Process Monitor will show you all the reads and writes. And hey, it curiously says, Alice and Bob. Well, that's strange. So he can go ahead and dig into the directory and doesn't see it there. Still doesn't see it. There's actually a dir/r, which is about the only command in the command prompt, unless you jump into PowerShell, about the only command in the command prompt to actually show alternate data streams. By default, they're pretty much invisible. So now he sees the stream, he knows what's going on. One way we could up our game as Alice and Bob is instead of using something obvious like Alice says and Bob says, we can use GWIDs. And I like GWIDs from a covert channel perspective because usually an administrator sees a globally unique identifier and they go, it's got to be Windows, I'm not going to touch it. Which is great. You want them to back off. So we'll use a GWID, but at this point in time, Mordek's already on to us. So what are some of the things we can learn from this? One, system security cryptography. Awesome in .NET, makes encrypting, decrypting very, very easy. It's awesome namespace. Here's the code, if you guys are interested, which is part of interop services. By default, you can't write to ADS with .NET, because .NET blocks it. You actually have to go into Win32 API. One of the things a lot of people overlook in .NET is you can access the entire Windows 32 API utilizing interop services and importing the kernel DLL, which is pretty interesting. Allows us to do ADS, allows us to potentially do some more interesting things as we'll see. Some notes for attacker, obviously hiding arouses suspicion. If you got a base 64 value in a text file, a good administrator should go, wait a minute, what the hell are you doing? Interoperable functions. In terms of defense, it all comes down to periodically scanning. Anyone in this room checked their Windows servers recently to see if there's any ADS stuff on it? No, we don't think to. We're only looking for stuff, right? We're only looking for the things we know, but there could be anything in there. We would never know. Not sure if I should duck when I see you walk into the room. All right, so that was round one. Round two. I knew it. See, two of them now. Ay, ay, ay. This is a tough crowd. All right. More like so many in this room, likes himself some Star Wars. Maybe not as much as Kelman, but he really likes it. Unlike most people in this room, right, because we're all pretty mellow, pretty low-key, pretty humble. But Mordek's not. He's got a good ego. So round two is Mordek strikes back. What we're going to do with Mordek is we're going to intercept some information from memory, and then we're going to mess with WPF. Important thing to note is this really is a fight between Alice and Bob. Sometimes Alice is attacking. I'm sorry, Alice and Mordek. Sometimes Mordek is attacking, and they're going back and forth. And in this particular episode, Mordek is definitely on the offense. So we are using a tool freely available called FTK Imager, which will grab a dump of memory and allow us to analyze it. And this is, in terms of recording these demos, this part actually took me about a day to record all these sections because it takes forever to get the memory out. So be thankful. We'll be sitting here watching a progress bar, and you guys will be really, really bored. But the key thing about crypto is no one brute forces crypto. I mean, maybe if you're the NSA and you got a bunch of compute power, but no one in this room or at this conference is going to brute force crypto, right? It just isn't the way it works. What are you going to do? You're going to steal the passphrase out of memory, or you're going to try and get the information when it's decrypted. So the first thing we're going to do is look for that passphrase. Now remember I said it's a system security string. It's not in here, Alice would tell you. But wait a minute. Yeah, it is. There it is. There's the passphrase right there. But the Microsoft documentation told me it wouldn't be in memory. But there it is. Now why is that? Well, the reason why that is we're using WPF for these ADS forms. And WPF leaks stuff all over the memory like crazy. So even if you're using secure code, it oftentimes is still in your memory. So Alice may catch on. She's like, I don't want him using FTK Imager. I'm going to wait till he logs off. So we'll let Mordek log off, and Alice and Bob can go back to chatting. And I'm going to show you something that the first time that I realized this when we were considering cloud computing, it really chilled my blood. Because here we've got Alice and Bob. They're on terminal server. This is a Hyper-V instance. I didn't mention that earlier. And Mordek has access to Hyper-V. So what can he do? He can save a VM, which is the same thing as saving your workstation. That dumps everything to memory. This part is not sped up, and I want you to watch this terminal window back here. So he's going to save it, and he's going to resume it. When you save it, it flushes all memory to disk. And now he resumes it, and now it's back up. You notice that terminal server window never closed. It would just pause for a moment and then pick back up and send data. So imagine your web server in the cloud. Imagine your database in the cloud. All these instances in the cloud. Is anyone going to notice if someone paused your VM? No. And once you've got it paused, you can copy that memory file and start looking at it. First thing we got to do when we've got it paused is actually extract it to a dump format. What we're doing there to, I think I'll pull it up in a second. Pull it up. Nothing like talking to yourself on a demo. So what we do to rehydrate it is use this command down here, if you guys can see it. The tool is called VM2DMP, cleverly named because it takes a VM and turns it to a dump file. Yeah. It's a free tool, available from Microsoft as a debugging tool. Once we get it in the VM2DMP format, we can look at it with something like volatility. Do I got any volatility fans in the audience? Anyone here use? All right, yeah. That's an awesome tool. You don't count. I didn't ask you. No, you count. You're awesome. It's all good. So what volatility can do is it can pull data out of dump files, right? So we're going to do 4 things from this dump file as soon as I rerun the command. We're going to pull out the active processes, the memory for the entire system, shared memory, the EXEs for all the active processes if we want to reverse the code, and we're also going to pull out the specific process memory. Why is that important? Because you don't attack crypto. You attack the key, which we already saw, or you get it in clear text. If the app is displaying it, it's already available in clear text in memory. So we use volatility to scroll through and pull all this information out. And then once that's done, all we have to do is use a tool like strings. So Mordek will jump on. Mordek will use strings. Mordek, like anyone else, Googles himself first. Come on, Mordek, catch up. And you'll watch up here as he types in the strings command and points it at the process ID 1996, which happened to be that alternate data stream chat window. And boom, there comes our chat windows, their chat messages, decrypted, clear text, of course, because they're displayed in WPF. Game over. So we've stolen the key. We've stolen the message in clear text. We can now look at what's going on. But, you know, that's not enough for Mordek. He's got to do just a little bit more. Got to get his kicks in. One thing we can do is use a tool called Snoop. Snoop, again, is free. It's up on Codeplex. The thing to realize with WPF apps, just like Windows Forms apps, right? This is all a common bus for communicating with your UI elements. So using a tool like Snoop, you can snoop into or look into an active running WPF app. And you can see the buttons, you can see the text fields. There it all is. You can see everything. Not only can you see it, but you can change it. You can insert messages into that chat stream. So maybe Mordek would want to, talk for Bob. Hey, let's tell Mordek everything. Alice, what do you think? Everything is right there available to us. So some notes for attacker. I mean, obviously, stuff is available in memory. Even stuff you don't think is available in memory. And the key thing, which I think is pretty fun, is WPF tampering, spoofing, very, very easy using tools like Snoop. On the defensive side, there's a lot of security features within .NET, like secure string, which is great. And you read the documentation, you think, I'm good, this is great. And then you sit down with a good friend from MySec at a coffee shop, and he goes, what, you just read the documentation? Let me see that. But not that that happened to me, but that could happen in theory. Because it needs to be trusted. Whatever your security system is, it needs to be trusted. A bonus note for anyone considering cloud computing infrastructure as a service, you have to ask yourself, who owns that hypervisor? Who can access that memory? And do I have any controls, both legal or administrative, to prevent them from dumping that to memory and pulling out sensitive information? Round 3. I like Alice. I like the fact she punches people and they die when she gets mad. I appreciate that. It reminds me of my daughter. It's a good thing. So, round 3, to the lolcats. To the lolcats go the spoils. So we've got an issue with Alice. She can't keep writing to the data stream, of course, because Mordek can see that. That's not cool. He can't write to text files because he's looking at that. So we're going to use steganography, specifically a picture of a lolcat. As you guys probably know, bitmaps are 24-bit, right, RGB, so 3 bytes. So if you take an encrypted message and you take out 1 bit at a time and write it into each one of those pixels, it takes around 200 to 300 pixels for the Twitter-sized message. But you can write it right into that file, and you can do it so in such a way that doesn't visually change the color. You can do so in a way that doesn't change the file size, obviously, because we're only messing with bits within the file. And you can also do some clever things where you spoof the dates on files, the created, modified, etc., as we'll see. So here we got Alice. She wrote her message into the file. And now Bob will go in and pull that message out. Again, B for Bob is passphrase. Path to the file. Oh, and the byte offset. So one of the ways people will attempt to figure out their steganography is looking at certain parts of the bitmap to figure out if there actually was a file or some data put in there. So we can stick it, right now I'm just arbitrarily using 1024, but you can stick it anywhere in the file as long as there's enough pixels at the end of the file to finish the message. Now Mordek, if he's still using process monitor, sees, hey, we've got people reading and writing to this file. So that doesn't make much sense. And he can jump to the file and take a look at it. But he sees, hey, wait a minute. The dates haven't changed. It hasn't been read or written to in a couple years. That doesn't make much sense. So what's going on here? He knows, of course, that people are reading and writing. So he's going to use something called PowerShell Common Extension, PSCX. Did I get that right? PSCX. I'm not going much in PowerShell on this. We've got a great talk in PowerShell with Matt coming up. But we're going to use get hash to get an MD5 hash, right? So with MD5 hash, as you guys know, small changes in the input file creates big changes in the hash. So run MD5, and that'll tell us whether or not this file is being changed. So Mordek can keep these hashes and keep looking. And sure enough, the next time Mordek runs it, there's been a change. But that only tells us, did the file change? It doesn't tell us who changed it, why they changed it, what they changed, anything else. So for that, we can use a detective control. We go into NTFS and go into the audit settings, and we can audit for either specific people. In this example, we'll audit for everyone. So we'll look at everyone and say, hey, what are they doing? Successes and failures. Now we've got to do one more setting, and that is in either the local security policy or the domain security policy, depending on how you're set up, and tell Windows where those audit entries should go. Here we're going to write them to the event log. Successes, failures, right into the log. And the next time Alice goes to do anything, that'll bubble up through the event system and be present in the security log. And now we can see who was it? It was Alice with the candlestick in the library. No, so Alice was clearly modifying the write attribute, right? The date it was written to. So how did she do that? How did that work? One way we can do to figure out what a .NET app is using or doing is use a tool called .peek. .peek is also free, and it'll allow you to drill into the source code of any .NET app, expand it, and decompile it, and see exactly what's going on. So here we see we're modifying the file dates, writing stego in, and then going ahead and spoofing it. Like I said, he loves himself some Star Wars. So, some attack notes. Steganography, especially least significant bit, 1 bit at a time, very, very easy to create, very, very easy to do. And source code, if you're in a hostile environment, your source code is open for anyone to look at if you're using .NET because of the way it compiles. And from a defensive perspective, it's hard to detect that. So really what we need to do is we need to always be logging. It's the old security maxim, right? Prevention is ideal, detection is a must. We can't necessarily prevent a lot of these communication channels. Why? Because they're for legitimate business use. But we can and absolutely should be detecting using audit controls. So let's go to round 4. Poor Alice. I mean, she can't write anything to the file system anymore without Mordek knowing about it. That's got to be frustrating. So let's take it off the file system. There is a thing in .NET called a memory mapped file. For those of you classically trained in comp sci, that's nothing more than a mutex. You grab a pointer to a chunk of memory and start reading and writing to that chunk of memory as if it was a file. So I also can do set this communication channel up. Now, if we just read and wrote our message in clear text Unicode, that's going to be very obvious. So we'll encrypt it, of course. That makes sense. We're also going to use that same least significant bit technique. But you're thinking, there's no bitmap in memory, so what are you using? Rather than actually using assigned bytes from a file, we'll randomly create bytes. So we'll create a whole bunch of bytes, 1 byte for every bit in encrypted message, and then embed our message within there. And on the Bob side, Bob can go in, he can log in, check that out. Now this can't be controlled by access control, which is good. Can't be detected by security control because it's not touching the file system, which is good. It's not going to show up in the event log or be otherwise apparent, which is pretty good, pretty good. Pretty good way to avoid Mordac, I think. And if he looks, again, at the file system, he's not going to see anything. If he drills into some system internal tools, there's a tool called WinOBJ. WinOBJ will show you all your objects that are open, right? All your mutexes and whatnot. Now, you may notice up front that we used a GUID for our mutexes. I think I mentioned that GUIDs are awesome because they scare administrators. And you can see why. There's GUIDs all over the place. So here is the base named objects. And before I point it out, does anyone see where that GUID is? Ah, too late. I pointed it out. But you see the point is that it blends in with like everything else. So the chance of an administrator seeing that is probably pretty slight. Now, if you dump that out to memory, we can take a look at that message. So we use, again, FTK Imager. Take a snapshot of memory, which I won't make you guys sit through that progress bar again. And then we will bind it as a evidence file. And then we'll search for that GUID. And we search for it and look at it in memory. You'll see, again, it is an encrypted value, which is good. It's pretty obvious it's encrypted. But you can also see all the random. Is my pointer working? Can you guys see that? All the random bytes down there. So around 400 random bytes of information. At that point in time where it's like, hey, you know, source code. I used this trick before. I know what to do. So one thing about .NET is, of course, that you can browse the source code, but of course the opposite thing about .NET is you can obfuscate the source code using a tool called Babel4.net. This is free on a trial basis. I think it's a 90-day free trial if you guys want to download it. You can create a Babel solution, which can include lots of executables, or you can simply just Babel one file, or you can babble on while you wait for the demo to catch up to you. Once you select your file, you can set different options, such as what you want to do with strings, how many passes should go on, what other sort of obfuscation techniques you want to deploy. You see here we're XORing, we're going 4 passes. And we'll go ahead and run it over the executable. And that's going to change all the function names, the pointers, and the strings. So when Mordac goes in and runs .peek, you may remember last time we ran .peek, we had really friendly names like steganography, don't look here, this is junk code Wolf needs to remove, things like that. But now when we expand it, you see we've got some weird object names that can't be read. What they are is just basic Unicode bytes. And we decompile the main method, hey, because I can read that one. We'll look and see that not only are the methods messed up, but also all the strings are also XORed with a value that's hidden in the header of the application. Which is good. It makes it very hard to view that source. It'll slow down Mordac, which is even more important. And it buys us some time. So in terms of attack notes, that least significant bit is usually only applied to images in steganography, but you can use it anywhere. And of course, it doesn't have to be the first bit. It can be any one of the bits. But creating a whole bunch of random information is very useful from a covert channels perspective. We want to hide amongst the noise. And of course, the memory is very, very noisy. This is the needle in the haystack principle, right? We want to have a good haystack. If you have a covert channel that's labeled, my mutex is Alice talking to Bob, and your message is in Unicode, clear text, you know, you basically have a needle in the haystack that looks something like this. And even The slowest Windows administrator will eventually figure out, wait a minute, there's something wrong with this picture. I know, I've tried. We've sat with Microsoft. So we really want something more like this, right? Lots and lots and lots of hay, little needle. And you can make your own hay using random functions, which is very handy. This is actually the opposite of the signal-to-noise principle. We talk all the time, oh, there's too much noise in here, we got to boost the signal. But when we're being covert, we actually want lots and lots and lots of noise, teeny tiny signal, to ensure that we're getting overlooked. I mean, you can do the math. 96 bytes, you the memory. Probably pretty safe. On the defensive side, if you're in a hostile environment, obfuscate your code. And a key thing here is, and I know Raph talked about it in his talk, security is essentially slowing down the attacker. Do whatever it takes to slow him down. We're never going to prevent Mordek from eventually getting to Alice or vice versa, but we can add some time into it and buy some time to cover our tracks. Which gets us to round 5. Mordek's getting kind of tired of this. It's on a memory map. You can't see anything. Can't log it, can't prevent it. There's all these random bytes. You can't view the source code anymore. So he's going to take the hammer approach. And the hammer approach, of course, is app locker. Is anyone here using app locker in production? Awesome. So you guys might even already know this. So we've got our demo, and we're chit-chatting. We're going to enable app locker, because it's a standalone machine, we'll do it on the local policy, by turning on the rules to say, hey, yeah, enforce the rules on what can execute. And then we're going to add all the hashes for program files. The way AppLocker works is that when you go to execute some code, and that is through the UI or through the console, not through the Windows 32 API, which is an important caveat, it would check the hash using the identity service. If the hash is listed and allowed, it'll run the code. If not, it'll bubble up a message. So here we've added some rules. We've enabled the identity service, or we'll soon be doing so. And once this is done, it'll be a very good preventative control to keep Alice from running anything but what Mordek allows her to, or so Mordek thinks. And I'm not one to spoil Mordek's fun. But we all know Alice. She's not going to give up. And there's several different ways that you could defeat this. But let's first show what the error message is. If Alice goes to run memory map files again, you see it gives her an error message blocked by group policy. She might think, wait a minute, this is just on a command prompt. I remember this trick from 2003 when you had those old security projects where you could just go double-click the app directly. But you see, we're also getting the same message in the dialog box. So what to do? There's a couple cool things that you could do. You could use PowerSploit, which is really neat. You could take your .NET app, turn it into shellcode, execute it. That would be really elite. But Alice is more old school. She's going to go a little simpler. She's going to use an app that does work, such as Microsoft Word. So we'll launch Word. We'll save our file with some arbitrary name, such as Melissa. Let's use Melissa. That's a good name. Now we're going to go in and we're going to enable the developer ribbon, which for security purposes has been disabled by default. There we go. It's enabled. Now what that allows us to do is write macros. Cool. So what can we do with macros? Well, we'll create a macro. And we'll actually load a macro that's been written by someone else. In this particular case, Richard Vandenberg, based on some research by Dieter Stevens. Now all we have to do is paste that macro in. And the way this macro works is it actually makes use of a hole in AppLocker where a trusted application can pass in a message and say, hey, don't apply the security because you trust me. So trust by proxy. So we'll just simply run on that path, which is the memory map, and now Alice is back in business. That is bypassing AppLocker in 20 seconds, 30? And I liked it. That's all full of nostalgic goodness. I miss Melissa in the days when word macros were something we all talked about. I haven't heard a word macro at a security conference forever, so I'm trying to rectify that here. So I thank you guys for your patience. So yeah, word macros, basically the whole concept here is if you trust something and you trust it to tell it that it trusts something else, then there's always a way around the security. So defense perspective, I mean, it's a great control. It works awesome, but there's always a way for a determined attacker to get around it. Which gets us to round 6. So app blocker is not working well for Mordek. What we'll do is we'll separate Alice and Bob, right? Let's get rid of this terminal service environment. It's not working well. We'll put Alice on a VDI. We'll put Bob on another VDI instance. And we'll then see how they communicate back and forth. So here you say we've got 3 VMs, Alice, Bob, and Mordek. Mordek's still in his terminal. And Alice and Bob are in Windows 7 instances on a 192.168 address. And we'll just confirm Bob's set up the same way. One of the easiest ways to communicate with Windows, I mean, intrinsically, way back, even before Melissa, we had RPC, Remote Procedural Call, right? Which travels over SMB. It's the default protocol in Windows. It makes the Windows world work. And what's nice about RPC is, thankfully, the Microsoft developers have included a very simple object to use RPC. And it is a very simple object. All you simply do is point it to a different IP address, and it handles the retransmits. It handles basically all the message encoding, everything you need to worry about. So all we need to do is set up a namepipe server, which Alice already did, and we'll then log into that namepipe server using a namepipe client, which is that IP address of Alice. And we'll then be able to send chat messages, again, AES encrypted. So we encode in Unicode, encrypt in AES 128, embed an RPC packet, and we let Microsoft Windows do all the hard work. And we're going to just echo it to the screen in hexadecimal. You'll see why in a moment. RPC is very, very noisy. Lots and lots of RPC packets. So from a Nito and Hey perspective, it's pretty handy, which is a good thing. Confirm that Bob is getting those messages, and he is. All right, good deal. Now Mordek runs into his first problem. No, maybe not his first. Anyone try and packet capture off Hyper-V? Another one? Nah, see? Because you can't. I don't know why. At least in 2008, you can't put a network card into promiscuous mode, which is lame, right? I mean, they keep telling us, hey, the cloud's great. To the cloud. But then we can't packet capture? What is this? So we're going to help Mordek out, and I'm going to ask you guys all just to suspend disbelief a little bit. We're going to send these messages across the wire to Wireshark so you can see them. There are tools that can put Hyper-V into promiscuous mode or attach listeners, but they're all paid for tools, and I don't want to be shilling anyone. So we will help poor Mordek out and send him a message. And there's the message, and there it is encrypted. And I don't know if you guys can see this in the back, but in sending that message and then recording this demo, I've racked up 68,307 RPC messages to Mordek. Try finding a message in that. If you have a beard and your name is Wolfgang, you may spend all night trying to find it and then say, forget it, I'm going to use hex. Because if I've got the hex, I can find it. So there's the one packet out of all that that actually had the message. All the rest was the retransmits and other inter-process communication. But there you see the bytes. And again, from a Windows perspective, if you're a Windows admin, is an admin really going to know that that's not an RPC packet? No. Especially among 68,000? No. No way. So bonus note for the cloud. If you're in the cloud, not only do you have to worry about who has access to your hypervisor, you have to worry about, do I have access to my hypervisor? Can I sniff my packets? Can I look at the inter-VM communications, right? Because our densities now are reaching into the hundreds of thousands, so most of our communications are inter-hypervisor, right? They don't go over the physical network anymore. Something to ask your cloud vendor. From a attack perspective, this is all about, again, hiding amongst the noise. A typical financial services firm, which I may or may not know something about, sees around 600 million packets a day. 60% of those happen to be SMB RPC, which means 300 to 400 million packets a day. If someone's chit-chatting over RPC, are we going to pick that up? I don't think so. I actually was discussing this with a local MISA guy, Derek Thomas, who does network security monitoring. He's like, you know what I would do, man? I would just look at the entropy values in my IDS and it would pop right out. And I thought that was really cool. So let's explore that for just a minute. Entropy is the measure of information, right? The difference between randomness or the difference between all the same. It's a rolling average. So if we take the number 173, we can encode it in coin flips. And let's compare that entropy value to random. Number 173 running Shannon entropy is actually about 0.95. So it's about double that of random. So clearly there's probably some difference between that coin flip and random. But noise is our friend. So if we got only 8 coins, yeah, you could run entropy and say, wait a minute, that's 0.95, that's not random. But if we wanted it to be 50-50, all we have to do is double it, right? Just add another 8 coin flips and noise. So now for every head, we have a tail. Now for every tail, we have a head. For every one, we have a 0. And if you ran the entropy over that entire thing, signal and noise, now we've got an entropy value that spoofs random coin flips. So what does that have to do with RPC? Well, I think I clicked one too many times. Did it work? Well, the entropy, come on, don't be like that, Alice. Quick, someone throw a shmoo ball at me. Okay, good. So, thank you. You guys rock. Shiny. So we can use an entropy calculator that's within this .NET code. And it actually just simply runs the frequency of each character. So we can look at the frequency character and we can say, okay, this message, the frequency of each character in this message happens to be 4. All right, fine. That's not too interesting. What we can also do is look at our bytes and look at a comparison bytes, for example, packet capture of a valid RPC, and then run the entropy calculation against those two. So now we got an encrypted message. Here's our message. We're going to use the default, which in this particular app is RPC. And you see very quickly, was it 15 milliseconds, we have jumped the RPC up. In 15 milliseconds, we simply calculated a whole bunch of seemingly random bytes. These random bytes are based on the frequency of an RPC packet. So all we have is this blue, which is just like our coin flips. This blue is our message. All the rest is random. Now, you can have it go out till it fills and has the exact same entropy, or you can specify the value. In this particular case, I only did 1024 bytes. That jumps an encrypted message up from entropy value of 3.6 to 7.8, which is real close, well within range of the Shannon entropy value of RPC. And the next time you see D. Tom, I beat him. No, don't tell him that. He'll come back at me. The key thing here is that covert channels should mimic the entropy of the legitimate communication. So if we got lots of straw, we got a needle, we want that needle to look like straw. Let's go to round 7. Let's put in a firewall. The tricky thing about firewalls in .NET is that in order to pass communications that would bypass a firewall, we need to get a shell. We need to get admin access. A couple different ways you could get admin access. We could capture the password hashes from memory using volatility, which is awesome. There's the commands in case anyone's interested. The other thing we could do is execute some shellcode. I mentioned earlier that interop services is a lot of fun because, yeah, I like Alice's sense of humor. She's cool. Interop service is a lot of fun because we can run Win32 API. Win32 API, one of the things it can do is execute shellcode. That's one of the things that Windows does. So we'll do, what's the intrinsic demo, right? The key demo of shellcode. I got shell. What app? Come on, guys. Calculator, come on. Got to get a calculator. So run B, first demo. You'll see the shellcode pop up there in the background, and it'll fail because the execution has stopped working. But we've launched calculator as shellcode. Another demo we can do in terms of shellcode is launch an error message. Message box. I've got your box. And there's the actual shellcode that pops up this message. It says, I got you, this is malware. That honestly is as far as my pointy hair goes in shellcode. So you're going to have to give me some suspension of disbelief. But Alice could do a lot of different things to get access to her box. The key takeaway here is interop services is scary. It really is. It scares the death out of it. Because you can run shellcode, you can do anything Win32 API, and there are attacks like Powersploit and Social Engineering Toolkit where people now off the web, if you see Dave Kennedy's demos, he streams down shellcode, uses the exact same code as that was just displayed, and runs whatever he wants in your box. Also, this method bypasses AppLocker. So if AppLocker had prevented the calculator from popping up, it would still pop right back up. Scary, scary thing. So round 8. We keep throwing technical controls at Alice. She keeps punching through them. We're going to keep going at this. The quintessential demo for covert channels is ping, right? Because ping, we usually just think about it as, hey, we sent a ping. But of course, it can handle and carry any byte you want. One of the great demos I've seen in ping is actually using Scapy, right? So you use Scapy with Python. You can actually transfer out a whole file. You can do all sorts of different things. Here, with Alice and Bob, we're going to use ping, but we're going to send AES encrypted messages, embed them in ping packets, send them across the wire, and see what that looks like. Now, the problem is we can't add much noise, because ping packets by default are only 74 bytes in length. So it's not like we can add noise and kind of spoof the entropy. So that's kind of a weakness as opposed to RPC, which has lots and lots of range that we can put in. Now, you notice Bob is running as admin. He just put in his IP address, Alice's IP address. Now it's going to open up the socket. You see we get this ugly exception because sockets require admin access. That's why Alice had to blow a hole in the security in the last demo. And that's also why you've got to run some demos as administrator so that it can open up that access. So you run the console as admin. You log back in. And now this session will open, and now we can send ping packets back and forth. So we'll send our encrypted message. Make sure Bob gets them. Good. So ping works. Ping works. Ping's past most firewalls. They can carry anything you'd like. Pretty handy. In terms of defense, this is similar to what we talked about with the file system. We always want to be auditing. And a lot of people, not the people in this room, not the people in this crowd, but a lot of times if I'm at a network operations summit, they're like, what do you mean you watch your internal traffic? I only watch my firewall traffic. Why would you watch internal? I mean, most people are not packet capturing. And of the people who are, most are using NetFlow. So to put that differently, most people are blind, and the rest of them have glaucoma. Because it's bad. You can't see into the packets. You have no idea. Was that a real ping? Or was that a message? I have no idea. I can't tell. You can also not see things such as DNS, which we'll look at next. Alice. Yeah. Never stop improving. Round 9. We're going to use base 64. No, we can't. Base 64 won't pass DNS. We're going to use base 32 to encode and send some messages. I mentioned with RPC that all the message encoding was handled by Windows, which is nice. Windows does the retransmits, breaking up into fragments, all that sort of thing. Can't do that with DNS, because here what we're going to see is Alice is actually going to build a protocol within a protocol, which means we have to have some message encoding, some fragment IDs, some message IDs, what have you. So we're going to use base 32, which is 5 bits per character. 1 bit in each one is going to be our message encoding. So that will be our message ID, our fragment ID, what have you. And the other 4 bits will actually be the encrypted message. Does anyone have a time check? How am I doing on time at this point? 4 minutes? Okay. I'm going to jump. The way this looks is when you execute the command, it executes out to ipconfig, and passes out the messages. Because it's using ipconfig, it looks like any other DNS traffic, except for that's a very weird looking domain. One thing you'll notice is because we're encoding information, we get a lot of A's. In other words, a lot of zeros at the end. So we'll up our game a little bit by randomizing. Now we're sending out these messages in sequence, and you know, some smart people are going to say, wait a minute, your shortest message is always last. So there's obviously something going on. So we'll up our game a little bit more and randomly send out these randomized messages, which will be received. The first bit of every character will be looked at, and they'll be reassembled on the remote side. So that allows us to use DNS requests to pass firewalls. Called this Never Stop Improving because there's a certain home improvement store that actually was recently attacked. Credit cards were stolen, and how they get out, they used DNS in a very similar fashion using base 32. It's pretty interesting. From a defensive perspective, again, we want to do more than NetFlow. We need full packet capture. And we can also do things like looking for DNS with no response or some funky names, vowels, etc. That gets us around 10. It's also just about the end of my time. So we're going to leave it here. I think Alice and Bob had some really good red team and blue team. I really appreciate you guys letting me walk through it. I'd rather not know who wins. I'd rather just leave it a mystery and let them ride off in the sunset. After all, a good friend of mine, Nathan Ouellette, pointed out that really, it took you 10 rounds. If this was a real corporate environment, Alice and Bob would just use Dropbox. Okay, I can buy that. So let's do a wrap-up. When you're being covert, 4 main ideas. We want less signal, more noise, right? That's really covert. We want to mimic the entropy of our communication channel. Again, it's lots of hay, and when you pick up the needle, that's a needle that looks like a piece of hay. We want to decrease the likelihood of being identified using GUIDs and using naming conventions that blend in with other things. And we want to increase the time and effort it takes, once identified, for a defensive team to figure it out. Because they're under the same pressure as everyone else. Their wife's calling when you're coming home. Little Timmy wants to see you. And there's a good chance with that time pressure they may overlook and not get to your message. Here's the channels we went through today. Here's some of the attacks. Interop services, again, PowerSploit, check it out. PowerShell is awesome. Really scares me right now because there's no good controls for it. If anyone has any good controls, please hit me up. WPF tampering is really fun and easy. Snarfing things from memory. Always a good time. Anytime you can spend with volatility is a good day in my mind. And spoofing entropy to avoid IDS, IPS, and respond to DTOM, the DTOM threat. In terms of defense, we got crypto, we got secure strings, source code obfuscation. All it protects us and decreases the likelihood of being attacked. The key controls here are always audit controls. Audit your file system, audit your network, feed that information to a SIM. This actually came about initially because I was testing a SIM product, and I wanted a good way to beat up on that SIM. So as a reminder, all these attacks and everything were discovered by people with more time and talent than me. I'm not claiming to have invented any of these things. My main thing, my main contribution, as little as it is something called INCOG, which is a covert channels library. All the demos you saw today were part of INCOG. Those were released today at GrrCON, literally at lunch as we're uploading to GitHub like crazy, and they're telling me, no, use the other command, no, run it through PowerShell. But you did, you know. But it's up there if you guys want to grab it. It's available to hack away at it under the BSD license. There's my GitHub. There's my email. I want to thank you guys all. I hope you guys have a great GrrCON. Appreciate you coming out.